So in a sense, we're going to go a little bit backwards. We did two slits, and then we did single slits. But single slits, in some sense, if you think about the Hawkins wavelets, they're kind of like infinite slits, because each little bit of light coming through each part of the slit may interfere with another part of the slit. So now we're just going to go back and do 3 and 4 and 5. And what you'll end up with is the idea of a diffraction grating. So first, let's just imagine that I have the plain old ordinary double slit experiment. So I've got a screen that's some distance L away from a slit complex, which is just two teeny tiny slits, and they're separated by distance d. And this is the interference pattern, intensity pattern I find on the screen. So alternating bright and dark fringes. And let me just ask what would happen if I opened a third slit. So I'll go down, just to make my life easy, by the same distance. And remember, this is a cartoon. This is like, in real life, this is super small, right? And I'll open another slit D. So what happens here where I have constructive interference? So I have constructive interference in part because the path length difference from here to there is off by a factor, so I'll draw it again, can't see this too many times. So from here to here, I've got this little path length difference. Delta R is d sine theta, and that's equal to, for the first bright fringe, that would be 1 lambda, right? That would be 0 lambdas, that would be 2 lambdas, that would be minus 1 lambdas. Now I've opened a third slit that's d away, and in the small angle approximation, actually all these angles are the same. So what's the difference in between this pair of slits and that pair of slits? So as long as you remember this is a cartoon and that's really small and that's really big comparatively, what we get is delta R again is d sine theta. This is the delta R in between the middle slit and the lower slit. And because the geometry is exactly the same, it's also lambda. So in fact, what you get when you open this third slit is, and you could repeat the argument there and certainly there, is that we had constructive interference, we'll keep constructive interference. So the place where this argument doesn't quite work, and you're like, wow, 3 slits is the same as 2. So these are still, actually we won't draw it like that yet. So we still get constructive for the 3 slits, constructive, constructive, constructive. The place where this doesn't quite work is here, right? So think about what happens at one of the dark spots. At one of the dark spots, this and this are off by half a wavelength. So delta R in between the top slit and the second slit, we'll call it 1 and 2, is, as always, it's d sine theta. That's just the geometry. But for the first dark spot, what this is lambda over 2. They're half a wavelength apart. And what that means is that when I add them up, I get destructive interference. They're completely gone. Now I open this third slit. Well, the third slit is going to be adding to the other two, but the other two already cancel to 0. So in some sense, these two have already canceled each other out. And by opening the third slit, it's actually going to add light. So our loci of constructive interference are just going to end up being the intensity from one slit and one slit only. So in fact, there's a slight change, and we can see it qualitatively, and then I'll just say blah, blah, math, because the intensity patterns are kind of freaky, is that you can argue your way into imagining there's a pattern that looks like this. So the brights get brighter. I've opened a third slit. They're all 1 wavelength apart there, or 0 wavelengths apart for the central bright fringe. But then, instead of the perfect destructive interference, the opening of the third slit actually adds a little bit of light. So we can actually show this, and I'll save the demo for the end. But let's say that I repeated this argument over and over and over and over and over. So it turns out that what you would get is a really, really drastic enhancement of that same effect, where the brights get brighter, and then there's all this choppiness in between. So what you'll end up with, and I'll draw it really roughly now and show you guys the demo right after this, is that for a multiple slit array, otherwise known as a diffraction grating, I'll end up with a pattern that looks like this. So bright fringe, chop, 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 bright fringe, chop, 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 bright fringe, chop, chop, chop. And in the limit of a huge number of individual slits or grating elements, these will basically vanish, and you'll just end up with a whole bunch of little dots. Okay? And so this is nice. What you basically get is same equation for free. So for diffraction grating, the bright spots are still, m lambda is d sine theta. Okay. But in this case, the d is the distance in between any of the two peaks. So I'll sketch a little bit better than I did over there. So all these things are separated by distance d. Okay. And this, again, the m is what's called the order. So this would be the 0th order. Right fringe, this would be the 1st order. And this would be the 2nd order, and so on. So those are just the names of the peaks, 1st, 2nd, 3rd order. Okay, so basically we get to reuse this. Why you would want to use that, I will refer you to the math that we're about to show you guys. And then after that, I'll show some demos. So this is the mathematical expression for double slit interference pattern. You can actually make it look nicer, but you just want to scare you guys. And so this is double slit interference, and then this would be opening a 3rd slit. And what I'm going to do is just animate a whole bunch of them so you can see qualitatively what happens when you get out towards having a diffraction grating. So this is, again, an intensity pattern. The purple would be 2 slits, so this would be a location where you have total destructive interference. This would be the central bright fringe, so the 0th order bright spot, where both of the light rays come out of each slit and just travel straight ahead and constructively interfere. This is where the light coming from the top slit travels half a wavelength less than the bottom slit, full wavelength, 1.5 wavelengths, 2 wavelengths, 3, 4, 5 wavelengths. You see the point. So this is just 2 slits. And the first thing that happens when I open a 3rd one is you see that the 3rd slit actually does not ruin the constructive interference. In fact, it assists it. And I have pulled a little bit of a trick here. What would have happened otherwise is the total intensity of the bright fringes would have just gone off the chart. So I'm what's called normalizing it and keeping the peak intensity the same. But then you see what happens with the opening of the 3rd slit. What used to be a dark fringe is actually a little bit brighter, because that 3rd open slit has nothing to destructively interfere with it. So qualitatively 2, 3, 2, 3. So now what we're going to do is just animate this, and I'll push this off to the side, and you'll see what happens is more and more slits open. So that's 2, that's 3, 4, 5, and this is why diffraction gratings are pretty great. So the bright spots stay brighter. In fact, they would get brighter and brighter if I didn't normalize it to keep the same peak intensity. Whereas all of this stuff at the bottom, so this destructively interfering stuff, and mixed, not quite perfectly constructive or destructive, basically goes to nothing when I have a whole bunch of slits. So I think it's probably out at about like 12 or 13. And for a diffraction grating that has 300 slits per millimeter, this gets very, very sharp. So this is why these are very useful things. So now it's animating backwards, and we're closing slits. Okay, so here we are focused on the board again, and what I have is a couple of slits. So this is literally 2 slit interference. And what I'm going to do by clicking the wheel is open a 3rd slit, same distance away, a 4th slit, same distance away, a 5th one. And I think that's all we get. So what you can see is that, again, the bright spots should be in the exact same location. And then there should be all these intermediate smaller peaks that are dimmer and choppier. So this is getting towards a diffraction grating. So this is 5, and then this is 2. And what would be nice is if we had a whole bunch of gratings, which we do. And in fact, this is the lie that I kind of told you guys when we did this demo, when I was talking about prisms. We couldn't really use a prism to demonstrate this. But this is a gas lamp, so this is actually helium, and this is a diffraction grating. So this has 300 lines per millimeter. This is so finely ruled that you can really just like see through it. And in fact, what you can see is you can see the light coming out of the helium lamp. So just focus on maybe one of the lines, the brightest yellow one. So what you can see is the first order, second order, so that's straight through, 0th order, that's first order, and then over there is second order. And so what I could do is imagine that I measured these, and I did with some chalk on the ground. Call that 10.2 degrees to that line, and then 20.6, if I remember correctly, to that line. There's something else going on if you notice the other colors. So zoom in. So this is neat. We're going to do some so-called spectroscopy with this. This is just helium. We'll look at some other elements, and each element has its own fingerprint. But basically what I can do is I can figure out, based on the angles and the rulings on this, so the slit spacing, I could figure out what the wavelength of that light is. So we'll do that right now. And of course, always remember, kids, to turn your lasers and your gas discharge tubes off. They burn out pretty quickly. Okay. So just grant me this. And this is a diagram of that particular experiment. So there's the helium discharge tube. And then what we're doing is we're actually passing this through a grating. And there are 2 different types of grating. There are so-called reflection gratings and transmission gratings. So because the light's coming through like it is here, so this is a transmission grating. And then the camera was the screen. And so what we saw is for the yellow line, there was a peak there and a peak there, and keep going, a peak there. So that would be straight through, that would be order 0. That would be the first order, and that would be the second order. And this is the part where you just believe me. So I measured the angle to this, and that's theta 1, and that's 10.2 degrees, and then that's theta 2. And that's 20.6 degrees. So let's put some words on this too. This is basically the idea of spectroscopy again, is using these different angles to measure something that otherwise would be really difficult to measure, and we actually thought about it as near impossible, is the wavelength of light. So this is for those really bright yellow lines that you saw. So what we have is we saw 2 orders, first and second. And really the whole point of having 2 is it gives us multiple measurements. And we saw them at those 2 angles. I'm not going to repeat them. And this is the part that's a little bit different in between double slit and multiple slits, or diffraction gratings. In a diffraction grating, that's characterized by 300 lines per millimeter. Okay, so what you don't get, and you can imagine, realize why that's the case, is I'm not going to just tell you the distance in between the lines, partly because the number of lines that actually get lit up might change depending on the source. But this thing is characterized, and you can maybe see it. I don't know if it's focused. Yeah, 300 lines per millimeter. So that's the usual way that people give you information about a diffraction grating, lines per millimeter. And aside from that, really, we just get to use this. So it's still d sine theta. 1 for the first order would be, well, let me just write the general formula first, actually. So this is still true for the bright spots, where that's the order, and then that's technically the difference in between them. That's just not quite what we're given. So for the first order, we should look at this. So d, figure out what d is in a second, sine of theta 1, and then m is 1 because it's the first order. And this is what we want. So what is d? Well, the units tell us. So we have 300 lines per millimeter. So 1 over that would be millimeters per line. So 1/300th of a millimeter in between each line. And math happens, and that's 3.333333333 times 10 to the minus 6 meters. That's d. So that's the distance in between two lines. If there are 300 lines every millimeter, 1 over that would be the actual distance in between each line. So 10 to the minus 6. Okay. So got that. So now what we have is 3 microns, 3.33 microns, sine 10.2 degrees equals lambda. I'll call this like lambda our first measurement of that yellow line. And then math happens, and my calculator tells me that this equals 5.89 probably. Oh, there we go. 5.897 times 10 to the minus 7 meters. Your calculator doesn't know that we typically call these things nanometers, so move it over 2 to get nanometers. 589.7 nanometers is lambda 1. So that would be and the 1 I'm using to denote, that's the first measurement of our yellow line. Okay, so you could repeat this whole thing for lambda 2, so the second order fringe, and really that's just to get a second measurement. I would just leave that for you guys to do to make sure that you understand this right and put up the answer. So lambda 2, the second measurement of the second order interference peak, that's 587.5, which turns out to be shockingly exactly what that should be. Right? So the things to make sure that you're doing right is the conversions to nanometers, the understanding which angle to use, what actually is the distance, does that change as you go from one to another? So again, this is spectroscopy, and what we did is with a couple of chalk markings, you didn't do it, but you saw that it was easy enough to do. I was able to find the wavelength of that particular type of light.